All right, so 9.3 is separable differential equations, and these are one kind of differential equation. These are like the baby differential equations. They're the ones you can separate. So obviously there's differential equations that you can't separate. So how do you solve differential equations that you can't separate? Well, there's all kinds of different recipes to do that, but we won't get into that. There's also higher order differential equations where they're the second derivative and the third derivative. There's linear differential equations versus nonlinear differential equations. So there's all kinds of different differential equations. However, we're going to do the most basic. So here's a fundamental differential equation. dy dt. So y represents a population. It can be a population of bacteria. It's kind of bacteria, a population of a virus, I guess. So it's kind of poignant right now. So the instantaneous rate of change of a population, so y represents the population with respect to time, is ky. So it looks like it's Kentucky. So k is a constant. And constant, and y, of course, is the population. So the instantaneous rate of change of the population is proportional to the population. So dy dt is equal to ky. So we're going to separate this and solve it. So what do? We get the y's on one side, and then we get the t's on the other side of the equation, or the x's, depending upon the kind of equation it is. So we're going to multiply the dt over. So dy is equal to ky dt. Oh, that's supposed to be a t, dt. And then we're going to divide the y over. So 1 over y dy is equal to k dt. So we've separated the variables, and that's what the separable part means. We got the y's on one side of the equations, and we got the t's on the other side of the equation, or the x's. K, of course, is a number, and there's not a t there, but there could be a t equation. So now what we do is we do the opposite to each side of the equation to solve, right? So the opposite of the dy is to take the antiderivative. So we have a symbol for that, right? So we're going to do the antiderivative to each side of the equation, the integral. So the 1 over y is the natural log absolute value of y plus a constant. But then over here, it's also going to be plus a constant. So we're going to make it one constant together. So the t would be kt. Kt, as in kt. I know a kt. And then plus a constant. So we got one big constant here. So this side would be plus a constant. That side would be plus a constant. So we just make it one constant on one side of the equation. Then we have to solve for y if you can. Sometimes you can't on these, but this one you can. So the base on natural log is e. So we say absolute value of y is equal to e. This would be the exponent here. So it would be e to the kt plus c. All right. So when you multiply like bases, you add the exponents. So absolute value of y is equal to e to the kt times e to the c. Well, e to the c is just some constant, so we make that a constant again. So we have c e to the kt. And then the absolute value of y is the absolute value of y is the plus and minus thing. Well, the plus and minus thing gets absorbed in the c because it'd be plus or minus c, so it's just that's just c. So y is equal to c e to the kt. Now that's one way you can see this. In money situations, you would say the amount is equal to the principal e to the rt. So you have a starting amount, you have a rate of interest, and you have a final amount. So that matches with that. In the terms of biology, we use that y is equal to y initial e to the kt, where k is the growth rate or the decay rate. So if k is greater than 1, the thing is going up, k is less than 1, it's going down. But you have a starting amount, and you go that. So these exponential equations come from the differential equation, dy dt is equal to ky. So ky is the it's the constant times the population. So the instantaneous rate of change of the population is proportional to the population. Well, that makes total sense. The instantaneous rate of change of the population is proportional to the population. Well, this is just exponential growth, right? So if you make a graph of it, so you got this. So if you have low population, right? So y is your population and t is your time. If you have low population, you have low change. Right? The rate of change is low. So when you have a low population, the rate of change is low. But when you have a bigger population, the rate of change is bigger. So hence the instantaneous rate of change of the population is proportional to the population. This is how these could look. So this was a crazy one here, and I separated, got the y's on one side, and then I got the thetas on the other side. And this side here worked out really well to go through and the u substitution and back substitute it back in and get this here. But then over here, that antiderivative is not something that we've talked about. So we would go through this mystery step here, you would end up with this. And that's not necessarily so solvable by y, but that's would be the solution to this differential equation here. But that's just an example. You don't have to worry about that one. Let's look at example 2 here. So this is given an initial condition, so we can actually find out what c is. All right. So the first step is to separate, to get the y's on one side, the dy's on one side, the dx's on the other, and all that business. So here we go. So I'm going to multiply the y over. So I get y dy. I'm going to multiply the dx over. So I get natural log of x over x in dx. So there's the separation of variables. So this and this stayed on this side of the equation, and the y moved over here. Now we take the antiderivative of each side of the equation. That's a really crappy antiderivative. There we go. That's prettier. Alright, so this requires a u substitution. This one doesn't. That's just straight up 1/2 y squared plus a constant. And I'll combine the two constants together. Let's see. What's u going to be? U is just going to be natural log of x. Why is it the natural log of x? Because the derivative of this would be 1 over x. So I can do that substitution thing where du is equal to 1 over x dx. So all of that gets substituted in for du. So there's 1, we would put a 1 right there. 1 over x dx is du, and then you would have that as u. So we get integral u du. So, yes. I'm thinking for a second. I'm going to pause here while I think for a second. Okay, I'm back. So we get 1/2 y squared plus c is equal to 1/2 u squared plus second c. We call it c1 and c2. Right? Put the u back in. So we get 1/2 y squared is equal to 1/2 natural log of x squared, natural log of x squared, and then plus 1c. So there's 1c value here. Yes, there'd be 1c value because we're putting the c's together. So if I subtract the c over, c2 minus c1 is just another constant. All right. It's a little weird, and you got to get used to it, but this is kind of the way it works out. All right, now, at this point, before I solve for y, I'm going to go ahead and figure out what c is. So x is 1, that's x, right? And the output is y. So you put in an x, calculate, out comes y. So it's 1 comma 2. So put 1 in for x, y is 2. So this would be 1/2 2 squared. Okay, that would be 4 divided by 2 is 2 is equal to. Then put 1 in here, 1/2 natural log of 1 squared plus c. Natural log of 1 is 0. And that's kind of what, this would be a no calculator problem. That's just something you'd have to know. The natural log of 1 is 0 because e to the 0 power is 1. So natural log of 1, natural log of 1 is 0, so that goes away. So c is 2. So I'm going to put the 2 back in for this right here. So I have 1/2 y squared is equal to 1/2 natural log of x squared plus 2. Now I'm going to clear the fractions by multiplying everything by 2. So I got y squared is equal to natural log of x squared plus 4. Because you got to multiply this by 2, multiply this by 2, multiply that by 2. Now I'm going to take the square root. Now when you take the square root of y squared, you get plus or minus. So y is equal to plus or minus the square root natural log of x squared plus 4. Okay, now we can tell whether it's plus or minus because of that whole thing about throwing the stick in the stream and like where the solution goes. Well, where am I throwing the stick in the stream to create that Euler path? I'm throwing it in at the point 1, 2. That's my initial condition. Therefore, 1, 2 has to work in this final solution to this differential equation. Well, if I put 1 in here, I need to get 2 out, right? Because it would be 1, 2. If I put 1 here, then that would be 0, and at 4, square root of 4 is plus or minus 2. No, it needs to be positive 2, because 2 comes out when you put 1 in. So the negative solution is a bogus solution. It's the square root natural log of x squared plus 4. So that's the solution to the differential equation. So what do? We separated our variables, got the y's on one side, x's on the other, or in this example here, the y's on one side, theta's on the other, or this example here, the y's on one side, the t's on the other side of the equation. So you got to separate your variables, and that's the name of this section, the separable differential equations. So once you separate, you take the antiderivative of each side, which is done by whatever means you have to do, u substitution or whatever. You do get a constant on each side of the equation, but you combine those together to one constant. Now this is where I always figure out what the constant is if I got an initial condition. And then I figured it out that it was 2. C was 2, and then we solve for y. All right, so this one was solvable for y, where the other example wasn't. All right, so I want you to do page 600, 1 through 17 odd, and then skip 7 and 15 because those require something that we can't do. Now, I want you to try these, and then I'm gonna walk you through the solutions right now. So I have all the solutions figured out on this piece of paper right here, and I'm going to walk you through all the solutions. And but I want you to try the problems and then see what you need for help with the solution. All right. Now the first few. Well, number 5 you can't solve for y. It looks like all the other ones you can solve for them. Then 17 is fun. 17's fun. All right, so here they all are. Here's the first one, and here's the solution to it. So I'm going to adjust what I'm doing here. Let me do a cover page. And here's the problem. And another cover page. There it is. And I'm just going to walk you through these. I'm going to put this a little closer here. And hocus pocus focus. And focus. Okay, so here's how you do number 1. And it's 1 to 17, skipping 7 and 15. All right, so the first thing I did is separated the variables. That's what it looks like. Antiderivative. I brought that up, notice that. There's the correct antiderivative, and then I solve for y. Now there's no initial condition here, so it looks like I divided the negative over. When you divide the negative, the constant still stays a constant because you divide a negative into the, it's just like it absorbs it. And then I did the little flippy upside down because that's 1 over y, so I flipped each side of the equation upside down. Oops, flipped each side of the equation upside down, my bad. I don't think I got the whole thing on there. Okay, here's number 3. Okay, there's the original problem for number 3. I separated, so it looks like I divided the x over and multiplied the dx over. Took the antiderivative, so I would think about that as 1 and then 1 over x. There's going to be a natural log in this one. So I divided those. Antiderivative is that. And I got to do the antiderivative each of those, which would be x natural log absolute value plus the constant on each side. So put it together to one side. Multiply each side by 3. I notice that still stays a constant because 3 times a constant is still the constant. It's kind of like the concept of the speed of light. The speed of light plus 1 mile an hour is still the speed of light. And then take the cube root of each side of the equation. So there it is, cube root. Okay, number 5. So here's the original problem. And it looks like it's already separated. No, it's not separated. I got to multiply over, whoops. I'm going to multiply over the dx. I'm going to multiply over the dx. Multiply over the dx, take the antiderivative of each side. There they are. And then this one here, as much as you want to, you cannot solve it for y. So you're done right there. That's it. There's no way to get that isolated by itself. Okay, the next one is not 7, it's 9. So here's 9. So here's the original equation. Separating this would be interesting, wouldn't it? So I think I had to do some factoring to do that. I think I moved those two over to the other side and then factored it out. Oh, I did double factoring. That's what I did. So I factored a p out of those, and I factored 1 out of that. Oh, I did the factoring by grouping. So then I factor this out. So I get p plus 1 times that. So this times this makes the original. So that's kind of tricky. All right. I'm going to move this keyboard because it keeps running. Keep running into it. So that's tricky. That's factoring by grouping. Then move that over. Antiderivative of each side. So that's just the there's no really inside function because when the derivative of the inside is 1, that's not an inside function. So it's natural log plus the c. And then I did base e, exponent answer, and then subtract 1 over. Now, the c thing, I did the same trick as I did with the, whatchamacallit, where it's e to the c would just be the c in the front, and then that stays there. All right, now we get to find c, because there's an initial condition on number 11. And let's see, we're separated, got the x's and y's. Antiderivative. Now this is where I find c. Plug in 0 and -3, and I got c is 9/2. And then I just algebraically solved for y. And then, oh, this one, the negative one works. The negative one works because you take the square root, you get plus and minus, and then you put the initial condition in. So I notice -3 has to come out of the square root, so it has to be negative in the front. Okay, number 13, this one here, the u would come over, the t would come this way. So there it's separated. So you multiply that over, Antiderivative of secant squared is tangent, right? Derivative of tangent secant squared. And you get u squared, the c's on that side. Put the number in, 0, -5 was the initial condition. And then that gives you 25. Put it back in, take the square root, get the plus or minus, then you put the initial condition back in, And it has to be the negative one again, because notice the negative 5 is coming out of the square root, so it has to be the negative version. Okay, and the last one, it's real fun. It takes up the whole page. So let's see. So we separated it here. That's going to the antiderivative. That's natural log. A is just a constant. So I did this as cosine over sine because it's 1 over tangent. Did a u substitution. I got that after the u substitution. Then I did. I found c at this point. And I found c because that minus that's c. So I put that on the end. There's the c. Then what the heck did I do? Oh, I combined this all together into one thing, because when you multiply, or addition means multiplying, and then that means division, so that's one big thing there. Then what the heck did I do? Oh, let's see, I flipped that up and multiplied to get 4, and then I have natural logs. I did the anti-natural log of each side. Well, basically, if each side's natural log, then this has to equal that. So I did that here, and then I subtracted the a over. So that's an a. There's the answer of that one. That one's pretty tricky. So give those the old Harvard try, and now we've pretty much completed the syllabus for the AP Calc.